Okay, so today I will divide my talk into 4 parts. First part is short. It says who is Yang. Number 2, what is photovoltaic and why perovskite PV. And number 3 is the recent progress of perovskite PV at UCLA. And then the prospectus of PVSK means photovoltaic, perovskite photovoltaics. Okay, so let's get this started. And let me see. Okay, and so first, oops, I have some. Okay, so first, who is Yang? That's me, and this is me, and this is the door of my office. So if you want to find me at UCLA, it's very easy. You find the most beautiful door at UCLA, and it is my office. And then I built this door. It took me 4 or 5 years. Okay, can I suggest you mute your mic? Okay, good. So I built this door. It took me about 3, 4, maybe 5 years to do it. I have all the greeting cards from all over the world. But not necessarily greeting cards, but I also put important things on the door. So, for example, oops, it's freeze. Or oops. 1, 2, 3. Okay. So, okay, good. Now it works. So, for example, this is my poster of my talk, and this is the historical picture of President Richard Nixon and Chairman Mao. They visited the meeting in China 50 years ago. So I want to share with you that my computer is not listening to. Okay, this is the door. Okay, my office door. It leads to the future, and then and so just give you. I like to think out of the box. I don't quite follow the rules, and then I like to be unique. At least my research to be unique with research with impact. And Jingji mentioned about our citations. That's actually because we have good students and good group cultures make it happen. So here is this. I want to talk about what is photovoltaic, what is PV. Okay, before we talk about PV, we must understand what is the sunlight. So today I will give the talk 9% in English, 1% in Chinese, the important ones. Okay, so here it is the 6,000 degree, around 6,000 degree K black body radiation from the Planck equation. And then the yellow ones are the, let me please, the yellow ones are the solar spectra from the sun. It detects from in the space. The red one are the solar radiation after the atmosphere. Okay, so these are the, for example, this is CO2 peak. That's what the gas caused the global warming effect. And I often take a simple model proposed by Eli that he mentioned about a solar cell is a semiconductor which is highly fluorescent. When the sunlight hits the semiconductor, it generates electron hole pairs, and then we combine from fluorescence, very strong fluorescence, as strong as possible. And these electron hole pairs has 2 important things. One is constructed, the so-called quasi-Fermi level. So the quasi-Fermi level are the distribution function of the electrons and holes. And number 2, it opens so-called open circuit voltage. So this voltage actually is the driving force of the solar cell. And then important part is you have to establish the right contact, they call selective contact. So the contact, one contact allow electrons to pull back, pull out, the other one is allow hole to be pull out. So I have some, okay. And they often use a so-called water bucket model. So this red represent about the sunlight. The sunlight into the water bucket and collect the height of the water represent voltage. So this is a water pressure, is the voltage. And then this is a water flow. So the water flow will drive the spinning wheel. So if you turn down the water flow, your voltage will go up. If you open your water flow will be high, but your voltage will drop. So it's a balance between a voltage and a water flow. So over here, this is the IV curve. Typically in the lab, when we do the measurement, we scan the voltage and then we determine the IV curve. And the power conversion efficiency, that's most people concerned, is the current times the voltage times the fill factor. Fill factor is how good your device is being fabricated. So that's involve a lot of technical term, and I will just skip those technical terms today. And okay. And I do have, okay, now, okay. So here it is, open circuit voltage. You can find this equation in the typical textbook. It's related to the current divided by the photocurrent divided by the dark current. The dark current is how good your device being fabricated. Photocurrent is how much light generated electron-hole pairs. And Eli has proposed this equation. It says that the VOC is actually, the VOC maximum is this equation minus KT over log of external quantum efficiency of the photoluminescence. If this efficiency is 100%, which is 1, then you get maximum output voltage. So one can actually measure the, engineer your material to be as high fluorescence as possible by better crystal growth, by reducing the defects, by engineering the optical feedback of the mirrors. So on and so forth. Okay, so let me see. So important part of this is the so-called selective contact. So selective contact, for example, this is electron contact, and this is a hole contact. When the electron can flow, be collected by the metal, but the holes will be blocked. I want to emphasize that blocking hole is not trapping. Trapping and blocking are different. We have a Nature paper just published last week. It's talking about how to build an ideal selective contact. Okay, and the hole contact similarly. So this is a typical perovskite solar cell cross-section. So we have a layer of cathode, which is typically metal, and then typically ITO, and the electron transport layer, perovskite, hole transport layer, and the anode and metal on the top. It's a sandwich structure. So over here, this is a band structure again. That is the electron being collected by electron contact, and this is hole by hole contact. Okay. The types of solar cell, there are many different types. Silicon is the group 4. This is a group 4. Silicon is here. And a group 3,5 gallium arsenide, which is expensive but very high efficiency. There are 2,6 compounds, CIGS. We talk about CIGS later more. And there's a cat telluride. That's the first solar cell. The first solar, for your information, is the most profitable solar cell company in the world. And then there's a next generation solar cells, which is organic photovoltaic and perovskite photovoltaic that we are going to talk about perovskite today. We are not going to talk about organic. Okay, so global photovoltaic market, last year they have 153 gigawatt being installed. Okay, and it's tremendous growth. And we all, in order to cut down the CO2 emission, we must install about, I think it's at least 2 terawatts globally, cut down 30% of the emission. And the number might be wrong, but I want to share with you. Currently, with all the emission being cut down by the photovoltaic, only 2% of global CO2 emission being cut down by the current solar panels. So in order to cut down, I would say 30% or 50% CO2 emission, we have a long way to go. That's why silicon panel is great, but silicon panel cannot do everything. We need the next generation solar cell, which is low cost manufacture as well as high speed manufacture. The silicon process has many problems, pollutions. It creates a lot of pollutions, okay? And then it also requires high temperature such that one has to melt the CO2, the sand, and then pull the silicon ingot. So it was estimated the first 5-6 years of the silicon panel production, the electricity is being used to pay back the electricity of the manufacturer. Okay, so it also requires a lot of land because silicon requires a flat panel, otherwise the efficiency is not high. It cannot be curved shape. Okay, so therefore, in my group in 2007, we were working on organic photovoltaic, but in 2007, I start a project so-called Project X, that we form a team with 4 students. These are the 4 students. We like to find the next generation photovoltaic materials. And now 15 years has passed. We can see those students' achievement. And Vincent is a professor in cost. He will be professor in the University of Tokyo soon. Matt Allen is in Apple Computer and a very high-level management team. William started his own company in Taiwan, and Peter is a research director in a solar cell company in Taiwan. So they are doing very well. Indicate if a student willing to challenge themselves, and they have a tendency to go beyond what normal career path. That's 15 years has passed. We can see those has been evidenced. Okay, so this is what we did. We use a solution process with a hydrogen to prepare the precursor solution for the copper indium sulfur selenide. And ideally, we want to make CIGS, but we make CISS. And so if you look at the next slide, it's very similar to perovskite. We do the spin coating, layer by layer spin coating, and then we bake, we heat up. And then it's very stable, by the way, CIGS or CIGS, very stable in air. Once you make it, it's more or less air stable. And we put the CDS layer on top and the zinc oxide as a top contact electrode. So our group doing very well. We actually got a lot of funding to do this project. So in 2007, we start from 0. In 2011, we reach 11% efficiency. Okay, so while we are doing very well, let me see. While we are doing very well, in 2012, we decided to start perovskite research. The question is why? Because at the time, perovskite research only 6% efficiency. So I want to share with a student. So this is a sentence I want to speak in Chinese. 跟各位学生、年轻学生分享啊，机会来的时候一定要抓住。所以don't hesitate. When opportunity comes, you have to catch it. Okay, so this is how we do. So in 2012, we start perovskite research. And then in the past 10 years, now it's 2022, in 10 years, we publish a number of Science, Nature paper and Nature sister journal paper. We published a paper in Science about January this year. We also published a paper in Nature last week. It's a highly productive switch. So in 10 years, we published more than 100 papers and being cited by more than 25,000 times. So I consider this a pretty successful program, okay? And we must credit to people who has willing the courage to challenge. Professor Chen Qi now is in Beiligang, Professor Zhou Huanping is in PKU now, as well as Professor Liu Jingbi at the Chinese Academy of Science Semiconductor Institute. And of course, Jing Jing is a host, you know her, in Zhejiang University, and Wang Rui is in Westlake University. Plus, a lot of students participate in this program. So we are educational institute. So our goal is to educate students, to produce people for the art societies. I think from that part, we are doing very well. So now we have to talk about what and why metal halide perovskite solar cell. What is perovskite? And the challenge for commercializations. Okay. Perovskite solar cell have this structure called ABX3. So it is the it has this A is the methyl ammonium, and B is the lead or tin, and X is the halogen group, iodine, bromide, and chlorine. And you can see that the interesting part, I often give example. This is like a bird cage, 鸟笼. So 鸟笼理论. So the bird cage that the A molecule, A side molecule is locked inside. So it cannot be too big, otherwise the bird cage is broke and actually become a 2D material. It's too small, the bird will fly away. So it is a combination of that, and it's quite interesting. B is the lead, and then the X is the structure here. So it's highly ionic. It's a soft and easy polarized. So there's an interesting material science parameter called tolerance factor that so you can plug in your radius, and then you can measure that that for a good proboscis semiconductor, we measure semiconductor, black phase is a cubic structure. So methyl ammonia is turned out to be the right element, but there's a problem that we talk about later. And Fa is also okay, but it's a little bit pushing to the limit of being too big. Okay, so we talk more later on the tolerance factor limitation. And Professor Yan Yanfa, he did a calculation of that, and he said that this material is coupling the balance band maximum. So on the other hand, the balance band, and this is the conduction band. The balance band maximum is the from the iodine p orbital. This is the iodine p orbital coupling with the lead s orbital. So lead s orbital is the red pink color, the red color here. So it coupled from the balance band. And on the other hand, is the lead p orbital. Lead p orbital is here from the conduction band. So the beauty of that is when Yan Yanfa did a calculation, he made me in conference say, Yang, work on this material. This is a dream material for people work on photovoltaic, because first is the red band gap. Number two, has no defects. You see the band is clean. This is clean. There's no defects there. Very defect tolerance. We know this material is very junky. You know, it's just solution process. Almost everyone can make it in the lab. Okay. And Professor Xiaoyang Zhu in Columbia University, he actually also shared with the community that this material is usually proposed a large proton model, extremely long carrier lifetime, because when one have a charge, you polarize the surrounding environment, and then equivalent force being shielded, the equivalent attraction force being shielded, you don't see each other. That's why extremely long carrier lifetime. So if you remember Eli's model, Eli's photovoltaic model, what you want is a semiconductor extremely high fluorescence and long carrier lifetime, so the carrier can find the selected contact to be pulled out. So those are the criteria being satisfied accidentally by proboscis materials. So look at this material. Proboscis is here, gallium arsenide is here. Proboscis band gap is tunable, and the absorption coefficient very high because of high density states. Carrier mobility for single crystal can up to 2,000, but 100 is sufficient. Long carrier lifetime, you can even up to microseconds if you purify material well. So that's why we talked about this already. So that's why the proboscis solar cell has been increased of efficiency so dramatically since it was discovered 2009. So this is a chart. Around 2009, Miyazaki in Japan started work on that, and then SKKU, Nanyu Park, and then our group joined in 2012. That's where it's about 6% efficiency. So you can see this efficiency in the next 4 years is really exponentially increased. Okay, and so our group joined this time. It's not too late, but you know, we have made a lot of progress. And then along the way, the efficiency has slowed down now, but still, right now it's 25.7%, reported by, I think it's by SOC. And this number of publications per year, I I do have a number, but I don't have around the room to put those numbers. I will update the slide next time. So if you want to be a faculty, this is the good area to be involved because the papers number grow exponentially quick. Okay, let's face reality. How can we realize the real application, commercial application? So it's cost, efficiency, and lifetime. So Professor Chen Qi published a paper 3 years ago. He did a calculation, but in his calculation, assuming 20 years lifetime for silicon and the proboscis. So actually, proboscis will be lower cost if same lifetime. And then the efficiency right now 20.5.7. I think proboscis will sooner or later catch up silicon because it's the right bandgap and better absorption and better mobility. Actually, not necessarily better mobility. And over here, the problem is stability. Less than 1 year, we heard that there are commercial companies like Xianna in Hangzhou. They report 25 years lifetime stability. But I really need to see, this is talking about scientific publication. We don't have that number, so I don't tend to cite that. Okay. So over here, my student Yeping Zhao, Dr. Yeping Zhao, helped me to summarize those 4 major elements of degradation. It is light, it is heat, it is bias, and moisture. All these things contribute to degradation, but you might think, wait a minute, for solar cells, it is light. And when you expose to light, it warms up, there's a heat and bias. These all 3 are photovoltaic materials and the devices. So it's true. What make proboscis successful also what killed it. So we see. Okay, now, so this is the metal halide proboscis under light. When you expose to light, what happens? You establish so-called open circuit voltage. Under the open circuit voltage, the ions, so this is the defects, by the way. Those are the halide vacancy, K-ion vacancies. Those are the material science terms indicate that the atomic site has been vacant. And those vacancies actually tend to be moved around under the influence of light and because of voltage. And there are chemical reactions because remember there's a TiO2 layer serve as a charge transport layer. When the light comes in, it has this catalytic reaction, trigger those chemical reactions. So sooner or later, your proboscis materials will have this HI, the 氢的碘酸 vaporize, and also this is CH3NH2 vaporize. So on the other hand, the material will escape from your device under the light, and that's not good. And under the heat, when you expose to light, it comes with the heat as well. So the heat actually speed up the process. You look at this black phase, cubic phase, but we heat up the material, and then you can see it become a yellow phase. That's a PBI2. Then that's what you vaporize those HI and the CH3NH2. So the cross-section SEM, you can see those voids that the material being vaporized close to the interface. So that's the heat. And then under the bias, you have the, so there's one experiment people have done that you take the parallel plate, parallel electrode, 这种平行电极, and then you put under the microscope, you look at the proboscis films. So you see that when the time goes by, you can see the ions accumulate near the interface, just like what we have here. So the ion accumulate near the interface of the metal and the proboscis. And this is similar research. Okay, so you can see this even faster, depends on the applied voltage. This one is 10 volts. Okay, over here is 1.2 volt per micron. Okay, so it depends on the unit. Okay, so the open circuit voltage also decrease under the condition because the material decomposes. Okay, and moisture. So the moisture comes in, decomposes the materials, and then this is the chemical reaction, again, becomes ions and then they move away. So these grain boundaries become channels, become rivers where moisture coming down, and then chemical reactions, so material disappear. So 4 major elements of that, and summarize. So ion migration is one of the major issues. By the way, ion migration is what we think, but there are fundamental reasons trace that. Either the material decompose, or their vacancies, or their chemical reactions, all kinds. Even moisture attack, but later it decomposes, it become ion, become form of ion. So that's why the major issue of proboscis are ion migration. There are many issues, but ion migration turn out to be what we have to solve. So I create a term called ion migration management. We cannot get rid of it because intrinsic property, because there are weak ionic bonds. Okay, and there are electron phonon interactions. They are hit because solar cell will heat up anyway. So you want to live long lifetime, we have to manage the ion migration and see how can we live with it. And overall, I consider device, the moisture attack, probably the easiest one to solve because you can just encapsulate. 你把器件封装了，应该就没问题. The question is how to do it economically, cheap enough. Okay, I'd like to thank Professor Dr. Ye Ping Zhao's suggestion of suggesting this table. Okay, so let's see the consequence of ion migration. You see, there are this paper by, I believe, Yan Yanfa as well. So you can see that there are material vaporized. Then you can see the voids, the grain boundaries. And there's a transport layer being degraded, okay? And there are phase degradation, so there are some area change the phase and the charge will dump into that if the band gap is smaller. And then there is the electrode, the ion migrate to electrode, they have interaction with the electrodes. Okay, so again, how to manage the ion migration become the key issues, okay? So in our group, we have spent past 10 years to study how to build an efficient device. In the early stage, we try to catch up the speed of the efficiency. And later we turn our attention, particularly under the DOE funding, that we try to stabilize the device. So we have studied how to pacify the defects, how to manage the grain boundaries, and then how to do the interface engineering. And today we're going to emphasize on the third part. But I want to tell you, proboscis is actually a very interesting material for the material science research, okay? And it applies almost all the textbook knowledge you need for material. So let me give you an example. This is work by my student Wang Rui and Dr. Jun Wu Li as well. That is the kinetic control of the crystallinity. So in material science, we know how to grow crystals. That is, there's the classical crystal growth theory. That is, your number of the atoms grows per minute or per unit time is related to your activation energy. The higher the activation energy, the slower your growth speed. So you see, we start to work on the so-called SEM base, form a dark phase. And Dr. Jun Wu Li started research, and then we try to slow down the growth so the material being better. So we put the MAI-PBI2 plus DMSO in the DMF solvent. So we slow down the growth process, and DMSO vaporize, and it become a black phase. And later, this technology was improved by Jing Jian and Wang Rui. They use caffeine to do that. And don't ask me how do they find the caffeine. I think they've realized from coffee. As Wang Rui, he is in Westlake, and why I know he drink coffee every day just like me, but he has a talent to come out caffeine. I don't. Okay, anyway. So that there's interaction, the CO in caffeine and proboscis, and found real bonds. So you can see from the FTIR, the caffeine and the MAPBI3 that led form a bonding. So this is signature bond. Because I did not intend to talk this part, I just want to tell you there are ways to control the crystal growth. We can grow very beautiful crystal. And this is just one example. So you can see the material with caffeine, the crystal grows, and then you reduce the grain boundary. So this is a cross section. This is the index. You can see that without caffeine, the silver electron actually migrates. This is the charge transport layer. You can see it, but with caffeine, your crystal is much solid. You don't see the ion migration. And similarly, you don't see the lead. Over here, you see some green color. That's the lead atoms through the charge transport layer. So the device stability is much better with caffeine, okay? So, so just give you an example. There are many ways to help the crystal growth, reduce grain boundaries. So those are the approach we try to manage, okay? And of course, we have caffeine. There are other people with some other molecules. So let's start my important part of my other recent research. The paper was published 2019. This one was just published 2 months ago. Is we start to think about A site. Remember, it is ABX3. So the A site cation, previously in Professor Yan's calculation, the A site only has a mechanical function. That's keep the crystal shape. But there are 2 A sites, remember. One is the bulk A site, the A site inside the material. The other one is surface A site. The surface A site has this molecule that you can allow you to do much bigger molecule to study its physical property and how to modulate that. And we show you, Jing Jin and Wang Rui published a paper in Science talk about the modulation of the band structure. Okay, so over here, again, this is a Torrance factor. So this is a Torrance factor that this is a conventional A site group. This is MA is here, and the FA is here. So let me bring the laser pointer again. I used laser pointer earlier, that some function doesn't work. Okay, so this is the nice molecule. But you see FA is already pushing to the big one. And the system is here to a small. Okay, so many development possible by utilizing the oversized or undersized cation. So you can fit oversized and undersized in one material. So the letters distort a little bit, but they can live together. And if really oversized, you can form 2D proboscis. And then in concert, the 3D proboscis, you can actually mix different sizes. There's called size engineering, if you like to know. I mean, I created a term, by the way. So, oh, okay, now it works. Okay, so let's take FAPBI3, for example. So the FAPBI3 is a hexagonal phase, it's a yellow phase. You heat up to 120 degrees C, it becomes a cubic. But unfortunately, the room temperature is very easy to go back. So FA is not stable, pure FA is not stable. So typically people do 2 things. One is a bulk control of free energy. They mix FA with cesium. So the Torrance factor are, you have 2 ends, but you bring them to closer to the center. Or you can have a hydrogen bond of the A site. And then, but hydrogen bonds is big. And one can also do the surface energy, free energy control. If you have, remember the Gibson free energy equation, the surface gives you a negative term. So the negative term actually reduce the surface energy, reduce the energy, free energy overall. And so put it here. So that's why Jing Jin's first project in our group was to synthesize nanocrystals. That's also because of high surface area, reduce the free energy as well. Become more stable, but device is not as efficient as unstable ones. Okay, so how can one choose the A site to manage or impede the ion migration? So you can have 2 A sites equally symmetry, but you look at the calculation, the ion move quite fast. How to read this data is actually like a picture frame. You take multiple exposure. So you take multiple exposure such that you look like a cartoon, it has ions move from one location, this location move towards here. And then over here, you put oversized, a little bit oversized molecule here, the ion has to detour, has to 绕道而行, so it takes a longer time, slow down the ion migration. One can put the 2D materials, 2D proboscis, put the material to form a 2D proboscis such that your grain boundary is bigger, so ion cannot cross the grain boundary. Okay, so, and then also you can do the substitutional doping or additive doping. That's how to manage the ion migration through the A-site engineering. Okay, and then finally, this one is all the raw record efficiency so far. It requires this, something happening interesting. Anyway, I don't know what happened. Okay, so all the world record requires those amines, ammonia treatment on the surface. We talk about that more later. And then this is Wang Rui and Jing Jing's paper in 2019 about secondary grain growth through the surface treatment. Okay, and later it has a band edge configuration through the large molecule for the A site. So A site has a lot. We talk about this one more in the next set of slides. So A site has a lot of interesting surface preservation function as well. So it plays an important role. Remember, I mentioned earlier, Bell Lab and IBM, they spent a lot of time in the 70s to do the surface interface engineering to form OMI contact and Schottky barrier, and in the 1970s. That's how the silicon devices are so good today. So one has to pay a price for that. So now I have to do these things. Okay. So now let's change the subject to can A-site molecule go beyond mechanical function? This is a paper and Jing Jing and Wang Rui, they published a year ago in Science. So they tried these 3 different A-site that hang with this big molecule. So this NH3 attached to alkyl chain. I could give an example just like fishing, 钓鱼. So 你那个钓鱼线必须要够长，那个鱼才会去咬那个饵. So I use this example. So you need like a fishing. Your fishing thread need to be long enough. The fish, you can reach the fish. So the first one is that is the PRA. Let's go to here. The PRA. You don't see that the density of state is hidden in the balance band. And then the PRMA is 2 carbons. It's longer, so it's extend. And the PREA are the 3 carbon. Okay, if you count this, okay, actually 1 carbon and 2 carbons. That you can see how the A-site molecule are able to modulate the band edge through the NH3 cations. Okay, so that's why we can see in the band gap, within the band gap, I'm struggling with my laser point and with the band gap here, as well as so we prove that one can modulate, but it's only on the surface. Well, surface is enough, okay? So because interface is very important. And so you can see that the bulk structure not change, but the interface are PRA, PRMA, PREA. You can see that top morphology are being modulated. And we take the FTIR data, you can see that they are bond forming, and the XPS showing the similar things. The PREA and PRMA, there are the color code. They have a shift from the reference, indicate their formation of the bonds. Okay. So important part is that the device, of course, is better. And then I want to share with you is the whole mobility has been increased by almost 20 times compared to the reference. So without that is 0.14, with that is 2.67 for the whole mobility. Okay, so that's a very important fundamental study. So indicate we can use the surface treatment to modulate at least the surface proboscis band structure. So you might wondering, why do we need that? In the future, if you want to do the gradient of the band structure, one can use that approach. Okay. So finally, I'd like to mention about the interface study. This is a Nature paper we just published last week. And I want to share with you, in the early days of the silicon technology, Bell Labs and IBM and Intel spent tremendous effort understand the interface, because you see a silicon crystal that's clipped off, they are dangling bonds, how to form a ohmic contact and Schottky barrier in the dangling bonds. That's become a technical important challenge, also fundamental science as well. Okay, so over the 3 years, all this record efficiency has to be treated by one of these amine group. And when people know that, so organic amino halides that are important, and they know that they become N-type. And this is a whole collecting, this is a whole transport layer, but this is also the N-type. So you're wondering why this N-type material near the whole transport. So, but when one create the world record efficient, what did you do? You go and rush publish the paper. We don't have time to sit down and think about how to do the detailed study of the interface effect. But that's why it led us to do that. Okay, so this ideal electron contact and hole contact, you see. So there's an electron blocking layer. I mentioned earlier, electron blocking is not electron trapping. So ideal selective contact is never easy to achieve. So I put the result first. I'll show the same slide later. So what happens through the surface treatment was they create a so-called a potential well. It's a trap for the electron for N-type material. So you have a high density of electrons near the interface, and the bands in the interface here. And same as, but what my student Sean and Ting managed to do is treat the interface such that it actually become a more ideal whole collecting contact. So, yeah. And then, so let's come down here. Okay, so I come back to this slide later because I'd like to, oops. Okay, so let's look at the UPS data. So this is a reference sample. This sample reference. Look at the black letters. The white one was arrow. So the treatment, the surface treatment by the surface, the amino group, actually make them more N-type. So Sean changed there to. So let's take OAI as example. The orange color, OAI is here. So they move over here. And but if you look at the reference, so what we want to choose is a more P-type material. So you look at OATSO, that's the blue curve, it's a blue curve. So you see the barrier is very small. So let's look at this is the KBFM data that's measure the work function. 4.69 EV is the reference. The OAI become 4.49, you see. Your work function reduced, become more N-type. OATSO is 4.77, is P-type. And but in fact, this number, these two numbers are the difference are very small. Okay. But you see the surface treatment did not grow the crystal. The crystal are more or less the same. So it's good. So that's why we can compare. Okay, so for the PO, solid state PO is a steady state PO is the other treatment where the N-type of P-type make the PO higher efficiency. And you also see the carrier lifetime is longer. And the efficiency are more or less the same, about 24% plus and minus 1% here, or 0.5% here. So OAI is similar to OATSO. OATSO is about, I would say, 0.5% higher than ONI. but the stability tells you a very different story. The stability with OATSO is much more stable compared to OAI. It's the brown color here. So indicate the ion migration happens, indicate there are, I show you the ion migrations, okay? So this is an open circuit condition test. This condition is much more harsh, okay? So over here is a cross-section SEM. You can see the OAI, actually, you can see the interface start to blur. It indicates there are some degradation. On the other hand, OATSO interface is very sharp, indicate that they're actually okay. And similarly, you can see that ion has been migrated. This is the bromine. You see the bromine here? You can see the huge bromine here, and that's the EDX. And similarly, OAI, the iodine is here, iodine is here. But once we put the OATSO here, you see very little, much less bromine ions and the iodine ions diffuse. It's interesting why that you do the interface management, you actually slow down the ion migration. So we talk about that later, but one important, very fancy equipment was done in SKKU by Professor Nanyu Park and the Professor Jingwu Li's group. They took our device, this slice, take a ion beam cutter, you cut the sample. They take a KBFM, very fancy equipment, they shine the light. So they are able to see a device operate the real condition. They actually see this is a color code, this is a work function data. You can see this is a spiral molecule, spiral is here, and the color suddenly changed. It changed from the this is CPD, the surface potential, contact potential. It suddenly changed polarity from positive to negative. On the other hand, OATSO, it did not change until to the electron contact, which that's okay, that's what we want. Okay, so that's how you can see that we are able to identify this pocket of negative charge. And the counterbalance is the positive charge over here. So that's why it's the mirror image over here. Similarly over here. We have not worked on this part yet. Okay, so ion migration. So that we did a calculation, DFT calculation. We actually was able to calculate the activation energy for the bromine under the negative condition is much lower activation. It means easier to diffuse. And then similarly, there's this is one is the intra lattice. There's extra lattice. It's moving much faster with lower activation energy. Okay, so back to this slide. So now we understand how this one interface being probed, and so we are able to propose a method to fix this interface accordingly. So this is a very nice research work done by our group, SKKU and the Westlake University. So hopefully we will have opportunity to work with ZJU University in the future. Okay, so outlook. So how is outlook goes? This is our research in the past few years. We published a journal paper, Nature Communication science paper here, Nature paper last week. It's a very productive team. The big question is, are we ready for commercial application? Okay, so my answer is that I put partially in Chinese. 我认为啊，2022年应该是钙钛矿商业化的原理，至少是布局的原理。Why? Because 现在是商业化的 because in the past, in Intel, they have actually IBM, they have a study, a technology from the lab bench, 一个技术啊，从实验室发现到商业化。平均要20年的时间，这是 Intel 的 data indicates with such big company with such rich finance that takes 20 years. Probosca has been early success due to we have a lot of technology bumping into it because, for example, organic photovoltaic and other things has all been helpfully to contribute to the Probosca technology. 所以呢，但是到现在为止已经10多年过去了，我认为是现在可以考虑商业化布局的时候。OK， 因为经过10多年的研究，我们知道它的问题出在什么地方，我们可以集中火力来解决问题。OK， so that's my conclusion, the outlook. So I think we see a lot of efforts in China as well as Europe and the USA, the people, the government putting money, the VC putting money to do it. I think that's why it is time. Ion migration is a major issue. Now we have to know how to manage that. Okay. I'd like to thank Yuanjun is here. Okay, so it says my internet connection is unstable. Hopefully you still can see me. And I took a leave of absence to Westlake University. I joined 西湖大学 as a 工学院创院院长 for a year and a half, almost a year and a half. And then I back to UCLA. So this photo I took last year. Our group has reduced from 30 people to 5 people. 我们只能说兵在精不在多. Okay, so these 5 people are fantastic. And then let me show you. But also we need more people. So the process of rebuilding the YY lab is amazing experience. And then I'd like to thank the Department of Energy support. And then, so I back to this chart. I want to share with you. So we start from 2012. I show you up to 2021 earlier. So this is 2022. So we continue to be highly productive with impact. That's what I'm looking into, with impact. Okay. And this is my group now. So we back to double digit. Okay, so let's work together to make the world a better place. And then I like to show my last slides. 谢谢浙江大学的邀请，欢迎将来有机会跟浙江大学交流。I want to offer to students in Zhejiang University. 在今年和明年我们都要收化学背景的学生，做有机的合成、无机的合成。我希望浙江大学的学生 ，good students willing to challenge yourself, apply UCLA. Okay. Also, we also looking for 2 postdocs. So if you like to come to America to explore yourself, please feel free to contact me. Anyway, I'd like to thank Jingjing arrangement and the things invitation. Thank you so much. I'm going to end up here and I open for questions. Thank you.